It's all good. It's all right. I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you to just bless our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I was feeling some residual guilt for not saying more about theory of linear independence with you. So we will kind of go back a bit, and because I think, properly speaking, the material I'm about to share with you probably belongs before this more complicated coordinate change stuff, right? And as you're reading this chapter, you'll notice I do have a couple of examples of coordinate change, and I even have one example of coordinate change in 2 dimensions where I actually draw the coordinate axes for both, so you can kind of see how all this stuff really makes sense in terms of real coordinate geometry. In a more perfect world, we would cover coordinate change in the sense of rotational coordinate change in high school mathematics. It'd be part of the regular curriculum. People should already know it geometrically much earlier, but we don't. So, I have to relegate it to an example in my linear notes. But anyway, so I want to talk about, so here's an elementary theorem. If L is from say V to W is, a linear map, and S is linearly dependent, subset of V, then L of S is linearly dependent. So that's something I probably should have proved day one in here when we were starting to talk back about these things, right? But I was just looking through the chapter in the midst of my office hour tutoring, and I stumbled upon this. I'm like, oh, I should talk about that. So this is very simple. So here's the proof. If, there exists C1, C2, dot, 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 let's see, say CK in the field, not all zero, right? Not all zero, such that the sum I equals 1 to k of Ci Si equals to 0 for some Si in S, then we can calculate, right? Then L of that sum, right, is equal to L of 0. But it's a linear transformation, and we know that 0 maps to 0, right? Because you can easily derive that from additivity, right? You know how to do that, right? L of 0 plus 0 equals L of 0, so, but, so it's just that, right? I mean, you got that, yeah. Okay, so, anyway, my point here is then by properties of linear transformation, of course, we can pull, right, the summation out, using additivity and homogeneity of the linear transformation. So therefore, L of S is linearly dependent, because we've just shown that there exists a non-trivial linear combination of vectors. What did I just say? Vectors in the image L of S. So that's one thing. Another basic thing that we should prove in here, right, is the interplay of the kernel and linear independence. So another theorem, kind of a counter theorem to this in some sense, theorem the following are equivalent. And if you read my notes, I say the following two things are equivalent. Like, wait a minute, what? No. For L, again, V to W, linear. Number one, L is injective. Number two, the kernel of L is just 0. And number three, if S is linearly independent, that implies that L of S is linearly independent. Now I might, yeah. So these are equivalent criterion for a linear map. So let's see if we can do some proving here, right? One implies two. How do we do that? So we suppose L is 1 to 1, right? Let X be an element of, well, first of all, L of 0 equals to 0, right? Therefore, the set containing 0 is a subset of the kernel. That direction of the containment we have. We're trying to prove equality of sets, so we should look at the other case, right? Consider X an element of the kernel then, right? Then what? L of X is equal to 0, right? But what did we just say? L of 0 is 0, right? Which implies X equals to 0 by injectivity. Consequently, thus, the kernel of L is equal to the, is just equal to 0, right? Pick anything in it, it has to be 0 by injectivity. Let's see if we can do 2 implies 3. Right? So we're doing what? Suppose the kernel of L is 0, right? Then what? We'd like to show that a linearly independent set maps to a linearly independent set, right? So we probably should suppose L is linearly independent, right? Consider linearly independent S a subset of V. All right. Let, S1 Sk be elements of S and Ci element of F, for which what? C1 S1 plus plus Ck Sk is equal to 0. Okay. Wait a minute, hold on. No. That's not what I want to check. What am I trying to show? I've assumed that S is linearly independent. I'm trying to check what? L of S is linearly independent. So I need to let, not this, but I need to pick, L of S1, L of S2, L of Sk, and L of S. And let C1, C2, Ck be in the field, such that what? Such that, C1 L of S1 plus C2 L of S2 plus plus Ck L of Sk, right? That's all equal to 0. But then what? Well, by properties of the linear map, I can regroup that. I can rewrite it as L of a single linear combination equal to 0, right? That is exactly L of C1S1 plus C2S2 plus da 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 plus CKSK equals to 0. But what does that mean? Well, that means that the whatever's going into the map is in the kernel. Right? This is in the kernel. Element of the kernel of L, which we're assuming is 0. Right? So therefore, C1S1 plus da 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 plus CKSK is equal to 0. But hey, what did we assume about S? We assumed S was linearly independent, right? So logically then it follows that the coefficients are then 0 by the linear independence of S. So that implies then that C1 equals to 0 all the way and down by linear independence of S. And that ends the proof, because at this point we've shown that an arbitrary linear combination of an arbitrary finite linear combination of vectors in the image of S necessarily must be the trivial combination if we presuppose that the kernel is 0. So that shows that 2 implies 3. So to complete the equivalence, if we can prove, right, if we can just prove that 3 implies 1, that gets everything, right? You know this?
3 implies 1.
Yeah, I mean, if I can prove 3 implies 1, then that logically is equivalent to 1 if and only if 2, 2 if and only if 3. You know, ever think about this? If you have 1, 2, and 3 logically, if you can prove this, and you can prove that, and you can prove that, then why is 2 imply 1? Well, 2 implies 1 because 2 implies 3, and 3 implies 1. Yeah. So it's when you're dealing with equivalences of multiple statements, sometimes it pays off to go in a loop rather than just trying to brute force prove the biconditionality of the statements each one at a time. Now, that said, there is often in practice in mathematics, there's something to be gained by proving the biconditionality of the statements in each step, because it gets you a more complete mental picture of the equivalence. Actually going through that proof, it helps you to understand why it is that those are the same thing mathematically. But anyway, we'll content ourselves with 3 implies 1 here. If we can, we'll try anyway. 3 implies 1. So what am I supposed to assume? I assume, right, assume S linear independent implies L of S linearly independent. I'm trying to show L is injective, right? So let X and Y be elements of V, and suppose L of X equals to L of Y, right? All right.
Trying to show that X equals 1.
Yeah, I'm trying to show that L. Yeah, I'm trying to show X. If I can show X equals to Y, then I've showed L is 1 to 1, right? So then what? I mean, the next thing I would do is like, okay, well then what? Well, that would give me L of, X minus Y is equal to 0.
So that's in the kernel.
Well, I don't have anything about the. I'm not. Yeah, I mean, if we were aiming for the kernel, then that would imply X minus Y is in the kernel, right? Indeed. But anyway, we're not. Okay, so great. We need to S linearly independent implies. Now can you tell me something logically we could do with this? Like Math 200 style. How about this? If S is not linearly, if S is linearly dependent, if L of S is linearly dependent, what's that called? I forget the name of these things. Contrapositive, that's right. So, does that help?
But we want to assume the first side in equation. You're not like contrapositive if we want to assume that L of S is linearly dependent.
Well, yeah, I mean, I have that this is true, you know? So, I mean, so, I mean, L of 0, I'm sorry, I don't feel like I'm spinning my wheels here. I might be stuck. I think I'm stuck, Ernesto. Sad, but true. Huh. I need to I guess if I consider maybe I should, the only thing I can think of is to, all right, so consider S equal to, say, x comma y. If that's linearly dependent, excuse me, if this is linearly independent, right, then L of C1x plus C2y, if that's linearly independent, then L of S is linearly independent, right? But L of x minus y equals to 0 shows that L of S is not linearly independent. Therefore, what? Therefore, S must be linearly dependent, since we get a contradiction elsewise, right?
Yeah.
And then, so thus, S is not linearly independent, hence y must be equal to like k times x for some, you know, k in the field, right? That's a theorem we have, that if you have a two vector set and it's linearly dependent, it must be that one vector is a linear multiple of the other. The multiple could be 0, right? But then what? Then L of there may yet be like this proof may yet bifurcate into the 0 and non-zero case or something. But I'm all right. So I'm not sure what the right way is to deal with that. I mean, I'd like to prove that k has to be equal to 1, you know? I mean, I need to prove that. So I have L of x minus kx, which of course is 1 minus k, times L of x is equal to 0. So this right here means either 1 minus k is equal to 0 or L of x is equal to 0, right? If k is equal to 1, we're done. If L of x is equal to 0, well, then I think we're also done, because we suppose that L of x well, L of x is equal to 0, which is equal to L of y, right? I'm sorry, wait, hold on a second. I'm still, what if L of x is equal to 0? So, it's probably already just sitting in front of us. I just don't see it. Oh. So we already know y is equal to kx, right? So L of y, L of kx, right? Which is kL of x, which is equal to k times 0, which is equal to 0. So we have, oh, well, yeah, I knew that already, dummy. Dang it. A stupid case.
Well, then x is a linearly independent set by itself. The set s equals x, which means that L of x has to be a linearly independent set, which means that constant times x can't be 0. I mean, constant times x is 0, and constant is 0.
Bother. I'm just trying to prove L is injective, right? I've picked x and y. So we've argued so far that it must be that S is set containing x and y is not linearly independent, which means that we have that y is equal to kx. But L of x minus y is 0, which means that 1 minus k times L of x is 0, which, again, when I have a scalar times a vector is 0, I either can have the scalar be 0 or the vector be 0. If the scalar is 0, then we're done, because that means k equals 1, y equals x, great. But if the vector is 0, why in that case? Why when L of x equals to 0 can I conclude that x is equal to y? Oh, you're saying that forces x to be 0. That's what we should hope, right?
Yeah.
This should force, let's think about that. It should force x equals to 0. Which then would mean y is also 0. Okay.
Yeah.
Why should that force x equals to 0? Because well, like you said, the set just containing x, if, like, well, let's suppose, towards a contradiction, right? L of x equals to 0, but x not equal to 0, all right? Then this is a linearly independent set. And yet, L of the set just containing x, which is the set containing L of x, which is the set containing 0, is a linearly independent set, which is, of course, a contradiction. I mean, it's linearly independent by our assumption. So therefore, x must be 0, which then means y equals 0, y equals x, we're done. Whew. Yeah, that's that. Man. These things are not hard until you get stuck on them, right? As soon as you get stuck on it, all of a sudden it's like, that seems really difficult. But it wasn't really difficult, was it? It's just, we got stuck.
Kind of take a picture.
Oh, absolutely. All right, so that was one little theoretical tidbit I wanted to circle back and talk about. So now we did that. Hooray, we can go on. All right, so let me talk just a little bit more about, here's V, linear transformation T. Over here you got W, right? And let's keep with the discussion last time, n-dimensional V, M as in mommy dimensional W for your codomain. Well, there are two sort of important subsets of any, for corresponding to a transformation, right? On the one hand, you've got kernel, right? Maybe I can draw it kind of like this. Somewhere through here, there's the kernel, right? And somewhere over in here, maybe you've got the image of T, or if you like, the range of T, right? These are subspaces, right? They're subspaces of those vector spaces. But on the other hand, we also have, what else do we got going on? Well, we've got our coordinate map phi beta. We got our coordinate map over here, phi gamma. And so down here, we've got, you know, Fn, and over here we've got our Fm, right? And down here we've got multiplication by, you know, L sub A, where A equals to the, you know, T beta gamma matrix, right? So here's a kind of easy theorem to prove. All right, here's the theorem. The null space of A, or in other words, the null space of the matrix T beta gamma, is equal to phi beta of the kernel of T. So if you want to study the kernel, if you want to study the kernel of a linear map, one strategy you can use is find the matrix of the map with respect to some pair bases and just look at the null space of the matrix. It reveals to you the nullity, the dimension of the kernel, just like that. Of course, you can also directly calculate what the kernel is and find a basis for it as an abstract subspace. So it's, you got choices. But on the flip side, the column space of the matrix, right, is the image under gamma of the range of T.
Can you remind me what the null space is?
So the null space of a matrix is like the null space of A is equal to like x in Fn such that Ax equals to 0. And the column space is the span of the columns, right? Okay. Now, notice that the coordinate maps are isomorphisms, right? Agree?
Sorry?
The coordinate maps are isomorphisms. So, you might remember that if we look at the reduced row echelon form of A, for example, how does it look? You've got like, 1, 1, da 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 1, right? And then so here you've got, let's say, k. Over here you've got n minus k, right? You have k pivots, k pivot columns, and then you've got other stuff over here, right? And you've got other stuff up here. It's complicated what exactly happens, but this much can be said. You have k pivot columns. They're the standard basis in the columns. Fine, ones with zeros, that's it. But counting, there's n columns. So if there's k pivot columns, there's n minus k non-pivots, right? And the story is that the column correspondence property that I talked to you about earlier semester says that any of these can be built as a linear combination of those guys. Great. But there's a sort of more kind of silly thing that you can just point out is that the number of pivots is equal to the dimension of the column space of A, right? And the number of non-pivots is equal to the number of free parameters in solution of Ax equals to 0, right? So if you solve Ax equals to 0, what you're going to find is you've got an infinite number of solutions sometimes, and you have as many parameters as you have non-pivot columns. So in other words, you have a unique solution to this equation if there are only pivot columns, right? If there are only pivot columns, the columns are linearly independent and there is no non-pivot column. But in this case, this is actually the dimension of the null space of A. So this is also called the rank of A. This is also called the nullity of A. That's matrix theory. This is the rank nullity theorem from matrix theory. There are other things you can say about matrix theory, right? Like the dimension of the row space is equal to the dimension of the column space, which is, I don't know. Well, I don't know what that means. It means something, but that's a different thing. Anyway, so notice, right, that since what does this mean? This means the dimension of the kernel and the dimension of the null space, the dimension of the range and the dimension of the column space are the same, right? So this is one way you can prove that the dimension of the kernel of T plus the dimension of the range of T is equal to, well, again, that's n minus k, and this is k, because they have the same dimension, right? So, and that's equal to n, which, by the way, is the dimension of v. So there's the rank nullity theorem. Now, if you look at my notes, I have a proof which is more linear algebraic in nature, which I'll let you read. Are we good?
Okay.
So one of the fundamental questions you can ask is like, given a linear transformation, is it an isomorphism? You know, and then you can ask a question, can I change a given map to make it into an isomorphism? So let me just pose that question. How can we modify T, v to w, to morph it, let's say, into an isomorphism? Well, here's the number one thing we can do that's like very silly. What if it's not onto? How can you make it map? How can you make the map onto?
By making the coordinate equal to it, right?
Yeah, right. Just swap out w for t of v, right? Yeah. Then voila, it's onto. You know, which is kind of silly, but there it is. But how to make it 1-to-1 though? Well, one thing you could do is you could find a subset of v such that, you know, t restricted to u is 1-to-1. That's one thing you could do. You could restrict the transformation to a subset of the vector space such that it's 1-to-1. So if you were going to do that, if you're just going to restrict it to a subspace, you'd have to be careful not to include any two elements in the kernel. Because if you do, those two elements in the kernel both map to 0, right? And if you want U to be like a subspace, then you better have 0 in there. So this, you know, you could look at a restriction, but the other thing you could do is to like change the nature of the domain entirely. So basically, you can picture V in terms of, I mean, I pictured the kernel there like this, right? That's the kernel. But the thing is, there are, if you move the kernel, if you add something to the kernel, then what it does is it like just shifts it. So you can actually kind of just like think about these would be like, you know, x plus the kernel. So those are additive cosets of the kernel from an algebraic perspective. And so in view of that picture, what U would look like is something that cuts each one of these cosets just once. The kind of U I'm talking about here would have to be something like, pictorially, it would have to be something like this. It would have to be like a cross section. A cross section of V, which doesn't cut through any kernel more than once. This, you see, the thing is, for even For an arbitrary map, if we just take a step away from, we're done with this, right? Yeah. This conversation can be had for maps. I'm talking about linear maps, but this conversation can be had for maps. If I just have any old a, I have a function. I've got a function b over here, right? I can have this conversation. What does it take for f to be an isomorphism? Excuse me, forget about isomorphism. What does it take for f to be a bijection? 1 to 1 and onto, right? So same, just make b equal f of a. We've got surjective. How to make f injective?
Like with the sign inverse.
Yeah, like with sign inverse. Well, the thing is,
Restrict the domain.
we have to restrict the domain. How do you do it? Well, the thing is, you can write a as equal to the union over f inverse of b, b an element of b, such that f inverse of b is non-empty. So the part of b, let's say here, f of a is this part, right? You're covering that part, right? The points in here they're mapped to from points over here, right? Now, if there's 1 point maps to here, 1 point here maps to 1 point here, if that's already the case, well, it's already 1 to 1. But if there's a point over here, which has come from an infinity of points over here, well, it's not 1 to 1. However, if you sort through it, this is a partition of A. It's called the fiber partition. You can partition A into the disjoint fibers of the map. And so the fibers of A might look like this. You know, there might be a fiber that looks like this, you know? I don't know. Like, the fibers of an arbitrary map, there could be one fiber that's like three-dimensional. It's like a cube.
And with fibers, you mean all the points that map to a certain point in B.
Yeah, f inverse of b would be equal to, you know, a in A, such that f of A is equal to b.
And we call that a fiber.
That's a fiber.
Okay.
The fibers of a linear map are far more boring. What does the fiber of a linear map look like? See, the fiber of a linear map, if we look at what is t inverse of a point in W, right? What is that? Well, that's x and v, right? Such that t of x equals to W, right? But the thing is, let's see here. How can I get this? Okay, so let me get back to here. So V, on the other hand, is equal to like the kernel of T, and then direct sum everything else. Now, I'm assuming finite dimensions, but you may not know what I mean here yet. So this is a subspace, right? And so this would just be like the span of, you know, v1 dot 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 v. Goodness gracious, I guess it's vk in my current vernacular because k was the dimension of the column space. So I can take a basis for the kernel, and then I can extend it to a basis for the whole space. If the kernel is k-dimensional, excuse me, if the kernel is n minus k-dimensional, then what's left is k. There's k-dimensional. I'm going back to the counting I used earlier in this lecture. So the dimension of the range is k. So my point to you here, what I'm trying to get at, is that if x is an element of V, then x is equal to x naught plus x1, where x naught is in the kernel and x1 is not an element of the kernel. So in view of that decomposition, notice that T inverse of W is equal to, what was it, x and v, such that T of x is equal to W, right? But what's x equal to? Well, you're talking about like T of x naught plus x1, right? But that's really just T of x1, because T of x naught is 0.
I was just still looking.
You're fine.
Why do we say v equals the direct sum of the kernel of v plus the kernel of w?
Oh, I'm arguing that the kernel,
Because every element in v can be decomposed as.
any element of V can be written as the sum of vectors which are in the kernel and vectors which are not in the kernel. And you can prove that the intersection of those two subspaces is 0.
But the elements that are not in the kernel are not elements of w.
Oh, my bad, not W. I mean to say larg. Anything, any other letter. Any other letter would have been lovely here. Like V, NC, as in V, not the kernel. Oh, that's kind of stupid. We use K for kernel. V and K, there we go. The North Korean part of the vector space. Where they sing poems to the dear leader and don't have food to eat, stuff like that. So it's okay, they're not watching. Or are they? Anyway, do I have any North Korean YouTube followers? Well, they wouldn't be able to comment, right? So anyway, my point to you is that W is fixed here, and what I'm trying to get to is that even though like the x naught could be anything, the x1 has to be uniquely fixed. And there can't be two different x1s which do it, because if there were, their difference would be in the kernel, which would be problematic for x1 being in v not the kernel. So anyway, what I am taking an awful long time to get to the point about here is that this is really equal to, you know, x naught plus x1 such that, you know, sorry, such that T of x1 equals to W and T of x naught is equal to 0. Which is to say, x1 is fixed here, which is to say that this is equal to x1 plus the kernel of T. So you see the fiber is an additive coset of the kernel, is my point.
And why is x1 fixed again? I know x1 maps to w.
Well, if T of x is equal to W, there has to exist some x1 in, so you know, x1
In v and k.
x1 in not the kernel, yeah, v and k.
But couldn't we have multiple of those? More than one in.
For different w's, but not for the same w. So my point to you is that like there is, for a given, you know, say this is a w in the range, right? There is a specific x1 here such that, you know, this whole x1 plus kernel t, it all maps to that one point there. And so like x1 in my other picture would have been one of these guys.
So if x2 maps to w, then x2 equals x1 plus an element of the kernel.
Yeah, right. So if we study fibers of a linear map, we find that we should be looking at additive cosets of the kernel. And this is part of the reason, ultimately, that the quotient space construction is interesting. What's the quotient space of a vector space? Well, you studied abstract algebra, so you already kind of know the song and dance here. It's the quotient space of a, should I say a ring? I don't know. What should I say? I suppose it's the factor group from one person. Well, let me just write down what it is. It is the quotient vector space. So if you have, now the quotient vector space does not have to be defined with respect to a linear transformation. I just think it's for me, it's most interesting in the context of the kernel being the subspace that we're taking the quotient by, because basically squashing the kernel, you're squashing the points which are, departing your map from injectivity. So if you can collapse the kernels, you're morphing your map into an injective map, because everything in the kernel is mapping to 0. So if you can make the whole thing that's mapping to 0 into one point by gluing them all together, you've made an injective map. So, but I guess before we can get there, we should define quotient space. So if V is vector space, if V has subspace, let's say U, then V by U is equal to x plus U, such that x is an element of V. And how do you add cosets? How do you add vectors in this wild new world of quotient vectors? Well,
X plus y.
Right. And how do you scalar multiply? You cx, right? And this notation gets really old, really fast. So instead of this, we write x bar equals to x plus u. And then we have the definitions x bar plus y bar equals to x plus y bar. Or c times x bar is equal to cx bar. And then that notation is ever so much more pleasant. But the explicit coset notation has its place, right? So fundamental theorem is that x bar equal to y bar if and only if what? Y minus x is an element of u. So x plus u is equal to y plus u only if the difference is in the subspace, right? So to prove that x bar equals to y bar, that means that x plus u is equal to y plus u, where u is a subspace of V, right? So for instance, x plus 0 equals to x is an element of x plus u, right? Therefore x is an element of y plus u. Hence, say thus, x is equal to y plus u1 for some u1 in u. What does that mean? That means that y minus x is equal to minus u1, which is again an element of u, right? Oh, yay. Okay, so that's that. So we just proved that the difference of y and x is an element of u. conversely, if we have y minus x as an element of u, then y minus x is equal to, let's say, u2 for some u2 in u, right? And let's see here, so let's just write it out. X plus u is equal to what? It's equal to x plus little u such that u is in u. But that is equal to what? This right here tells us what? This tells us that x is actually equal to y minus u2, right? So this is equal to y minus u2 minus, or rather plus u, right? Such that u is an element of u. But that's quite, and here's, okay, fine, a little bit of a leap right here, but not too big of a leap. That's the same as y plus u bar, such that u bar is an element of u, right? So I'm thinking of u bar is equal to u minus u2. Since u is totally free, u bar is also totally free. It's fairly clear that that's a one-to-one correspondence of elements of u. So that's a reasonable step. u2 is fixed here, but the u is completely free, so yeah. A little bit of hand waving, but there it is, and that is precisely what? Y plus u, right? So there you go. We've proved the equivalence of coset equality is judged by, inclusion of the difference of the representatives. So this is quotient space. So then the question is, if you're dealing with quotient space, well, how do you build a basis for quotient space? Right? Can I erase all this?
Sure.
Okay. Let me...
I think it is, right?
Yeah,
Okay.
yeah, towards the end. All right, so what was I going to say?
The basis of the quotient.
The basis for the quotient space, right. So if u is equal to the span of u1, u2, dot, 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 let's say uk for the sake of discussion, right? And, the dimension of V is equal to n, which is, let's say, strictly greater than k. Right? And let's suppose that this is a basis. This is a basis for u, okay? So the way I would construct a basis for the quotient space is I start by extending a basis for the subspace to the whole space. So extend this to to V. Let's call beta is equal to like beta u unioned with, let's say, V1, V2, dot, 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 dot. How many are there? Well, there should be Vn minus k since I started like that, right? That's the counting, right? These are where? These are not elements of U, right? By construction. Okay?
Yeah.
The only linear combination of those elements which is in U is 0. Now, so I would argue then that V